Hello everyone, welcome to Dr. Ravi's Academy. In today's virtual class, we will be deriving the expression for the Lame's equation applicable to thick cylinders. If the wall thickness of a cylinder is more than the internal radius, that is r by 10, then it is called a thick cylinder. So now let us consider a cylinder with your internal radius is, let us say it is r1, and our external radius is r2, and it is subjected to a fluid pressure P. And let us consider a length of L, that is a length of L. This length is L, and of course this is the thickness. You have, this is the thickness. It is subjected to a fluid pressure of P inside. Now, when the high pressure fluid is flowing through the pipeline, obviously the radial stresses are developed in the material, and let us derive the expression for the this thick cylinder stresses, that is Lame's equation. And in this we have one important assumption, that is epsilon L is a constant. So with this assumption, apart from this routine, material is homogeneous, isotropic, and it is loaded within the elastic limits. And apart from this, epsilon L is constant. Let us select an element at a distance r from the center, elemental thickness dr. I am splitting that, and let us see the element is like this. Length is L. Length is L, and here this is at a distance r, and elemental thickness is dr. Right? Now the stresses, let us represent the stresses. Because of the high pressure fluid inside the pipeline, the radial stresses are developed, and let us assume that the stress developed inside, it is exerting on the inner wall, is sigma r, and outside it is, let us treat that it is, there is a elemental increase, that is sigma r plus d sigma r is the stress acting from the top, and circumferential stress, that is sigma c. So let us write the sum of all the forces along the y direction, that is sigma fy is equals to 0. So here the forces contributed by sigma r acting upwards positive, and sigma r plus d sigma r is negative acting downwards, and sigma c also downwards. Let us write down these three terms with multiplying appropriate areas. Now first you write down sigma r. This is the stress, and the projected area is this is r plus r, it is 2r, and the length is L, it is 2rl. 2rl is the projected area, that is sigma r, which is acting upwards, and minus, this is minus sigma r plus d sigma r is the stress, and the area, you see that it is a dr plus dr, that is 2dr, r plus r, it is 2r. So 2 into r plus dr into L, that is length of this. This is what is the projected area from the top, right? Now you have a third term, that is again minus, that is sigma c into, it is a 2r into 2r, that is a 2, it is a 2dr into length L is equals to 0. You have three terms, 1, 2, 3, only three forces, and that is equal, that is in equilibrium, is equals to 0. Now let us expand this and observe carefully the common terms. You have 2, 2 and 2. L is also common, L, L, L. So write down the leftover terms. You have a sigma r into r, and this is minus, expand this. So sigma r into r, and plus it is a sigma r into dr plus d sigma r into r plus d sigma r into dr. With this it is completed. You can close the parenthesis brackets. Now it is last term is sigma c into, it is a dr is equals to 0. Here This is plus and this is minus. Multiplication of two elemental quantities also negligibly small, and you have only three terms left over. And these are three terms. You see that it is a minus of this dr. You can take a minus. It is a dr. You can take out, and you have sigma r plus sigma c. You have taken dr common, and the other term is minus d sigma r into r is equals to 0. So rewrite this equation in such a way, it is you take this one term the other side, it is dr into, it's minus a dr into sigma r plus sigma c is equals to, it is d sigma r into r. Now let us consider the strain, longitudinal strain. Write the expression for longitudinal strain, that is equals to, it is a longitudinal stress, that is sigma L by E minus your radial stress is compressive, so it is becomes a plus, so sigma R by E into mu minus the third stress, that is circumferential, it is again mu times sigma C by E. This is what is said to be constant, and this is constant, and you can rewrite it is mu by e also constant, and hardly you are left over with sigma r minus, it is sigma c is some constant, and you would like to consider sigma c value. This you can write it even sigma c minus sigma r is equals to constant value as 2a, and you can substitute sigma c is equals to, it is sigma r plus 2a into your equation, into this equation. Let us substitute this value. You have minus dr into sigma r, and sigma r you have, you can take out 2 outside, you have sigma r plus 2a, you can write down plus a in place of sigma c is equals to, it is a d sigma r into r. Now you can rewrite in such a way that it is dr, you can write down this, you can take to the right hand side, it becomes plus. Now it is a minus, if you write minus 2 dr by r is equals to d sigma r divided by sigma r plus a. Now integrating, what you have is this, you take left hand side, you have ln of sigma r plus a is equals to, it is a minus 2 ln r plus constant of integration ln some constant b. So this simplifies, you can write down minus, this becomes ln, it is r square, and this becomes a multiplication of this. The other side you have ln of sigma r plus a. Now you can withdraw the natural log. You have sigma r plus a is equals to, it is r square into b, and you can write down, it is sigma r is equals to, it is sigma r, this becomes minus 2, this is becomes b by r square, this becomes b by r square because power minus 2. So now we can write down, it is b square, or it is b by r square, it is minus a is equals to sigma r. This is the expression for the radial stress. If you substitute this, you are going to get circumferential stress. That circumferential stress is sigma c is equals to sigma r is plus 2a, that becomes plus a. So it is b by r square plus a. So this is the expression for the circumferential stress, and these two equations together are called Lame's equations. And here the boundary conditions for the radial stress is inside at r is equals to r1 you have a fluid pressure P, and outside when r is equals to r2, that pressure is atmospheric pressure, that is 0. So using that you can calculate two constants, that is a and b, and you can obtain the expression for the, or the values of circumferential stresses, and both are varying parabolically because it's r square term is there, is varying parabolically. So let us practice this. And of course, one of the very important theorem with respect to your academic exams as well as gate examination point of view. Thank you for watching this video.